Hello students, welcome to the online lecture series of St. Andrews Institute of Technology and Management, Gurugram. Myself Sudhinder Vats, Assistant Professor in ETCE department. So in this particular lecture, we will see differential pulse code modulation and delta modulation, which is a topic in Unit 4th of Communication Systems. So Dpcm and delta modulation are the extension of pulse code modulation, which we have already seen in the last lecture. Okay, so in PCM pulse code modulation, we encode the samples of the waveform independently of all the other samples. We encoded every sample with a combination of binary digits, that is 0 and 1, independently of the other samples. Every individual sample is encoded using the binary bits. It has been observed that when a voice or a video signal is sampled at a rate slightly higher than the Nyquist rate, that is 2 times of message frequency 2 FM, the resulting sample signal was found to exhibit a high correlation or the similarity between adjacent samples. Like if we were taking samples at different time instants, like if I take this, these are the samples like we done in sampling, pulse code modulations. So we took a number of samples which we quantized using several levels and represent them in binary bits. So as the frequency or the sampling rate is increased more than the Nyquist rate, that is 2 FM, so we will be having a large number of samples which have a very high correlation between adjacent samples, that is the most of the samples will be similar to each other. Okay, and there will be a very little difference between adjacent samples. So it means that the average change in amplitude between successive samples is relatively small. So the difference of amplitude between adjacent samples would be very small if the sampling rate is very high than the Nyquist rate. Or we can say that in pulse code modulation the redundant information is generated. Redundant means that the duplicate information is generated because many of the samples would have the identical in codes. So most of the samples would have similar sort of codes if the sampling rate is higher. So by removing this redundancy before encoding, we may obtain a more efficient coded signal. Efficient coded signal means we can generate a signal in which the large amount of information can be represented using a fewer number of bits. As the sampling rate is increasing in case of the pulse code modulation, so the quantization level would also increase and we would require a large number of bits to represent our coded samples. So by using the redundancy in these samples, we can generate a more efficient coded signal in which we would require a fewer number of bits to represent our samples before being transmitted. So hence an encoding scheme that exploits the redundancy in the samples and result in a lower bit rate for the source output is required. So we would use some encoding scheme so that we can reduce the bit rate or the number of bits used to represent our samples. Okay, so what is the principle of Dpcm is, in Dpcm we encode the difference between successive samples rather than the samples itself. So we decode the difference. As the difference between the adjacent samples is very low, we would encode that difference before transmission instead of the samples being encoded. So since difference between these samples are expected to be very small, then the actual sampled amplitudes, fewer bits would be required. So fewer bits would be required to represent the differences. So in this case we can quantize and transmit the differential signal sequence, which is the error signal, where xn is the sampled value of xt at any instant n, and xn minus 1 would be the value prior to that instant. That is, these are two adjacent sample values and we would transmit the difference between them, or we would generate the difference using the differential pulse called modulation. So this is the basic principle, that we would generate the difference between two adjacent sampled pulses. So here in this Dpcm circuit we would use a predictor. So why we would use that predictor is, when the sampling rate is set to at the Nyquist rate, it generates excessive quantization noise. So if the sampling rate is almost equal to the Nyquist rate, that is 2 times of FM, then there will be excessive quantization noise, which can be decreased by increasing the sampling rate. But as we increase the sampling rate, the bit rate would also increase. That is, the number of bits required to represent a particular sample would increase, and hence the bandwidth would also increase. So there would not be any difference between the Dpcm and Pcm. So it can be improved by recognizing the fact that there is a correlation between successive samples. There is a similarity between successive samples. Now a general approach is to predict the current samples based on the previous samples using linear prediction. So we will use linear prediction, which would predict the value of the sample based on the previous sample, or we can say we can predict the difference between the two successive pulses. Okay, so let's see how. So hence predictor is a device or something which can predict the range of next required increment to the past value in order to produce the present value. So predictor will predict the present value on based of the previous value. So it will predict the increment required in the past value to generate the present value. Okay, so this is the block diagram of a differential pulse code transmitter, in which we have a quantizer and a prediction filter, and obviously in the last we have a encoder. So the input signal or the input sample, that is x of NTS, is fed to this summer or the adder, and also the predicted input x cap NTS. So this is our predicted sample, which is predicted by this prediction filter. So the difference of this would be the prediction error, that is ENTS, and this E of NTS error is fed to the quantizer, which would generate the quantized error EQ and TS. So input to quantizer is given as error E and TS, which is equal to the difference of the sampled input and the predicted sample input, x of NTS minus x cap NTS. Where is the difference between quantized input sample x NTS and predicted one is the error. So the predicted value, that is x cap of NTS, is produced by using a prediction filter. With prediction filter, the consist of quantized version of message sample x and TS. Okay, so this is how this prediction filter would predict the sampled value x cap and TS, and it can be a comparator. This summer can be a comparator which compare the input sample x and TS and the predicted value x cap and TS, and give us the error, prediction error, which we will feed to the quantizer, and the quantizer will give us the quantized error output, which we will feed to this summer, and this sum will compare the predicted sample x cap and TS and the quantized error to generate the quantized sample xq and TS, which is fed to the prediction filter. Okay, so difference between the signal E and TS, the difference signal E and TS, which is generated by the sampled value and the predicted value, is called the prediction error, since it is the amount by which the prediction filter fails to predict the input exactly. So it is nothing but the difference or the margin by which our prediction filter misses the predicted value of the sample x and TS. Okay, so by encoding the quantizer output, we obtain a variation of PCM, which is called differential pulse code modulation. So we can see in this diagram, this quantized error EQ and TS is fed to the encoder, and encoder will give the output in form of this quantized error. So the encoder will now encode the quantized error instead of the quantized samples. So it will encode the quantized error, which is nothing but the difference between the sampled value and the predicted sample value. Okay, so the output of the quantizer is given as EQ and TS, which is nothing but error signal NTS plus Q of NTS, where Q and TS is the quantizer error. So Q and TS is the quantizer error. Hence the input to the predictor is XQ and TS, which is nothing but X cap and TS plus quantized error EQ and TS. Now from the above equations we would get that this quantized output XQ and TS would be equal to the X cap and TS plus error signal NTS plus Q and TS. So it would become this quantized sample XQ and TS is equal to the input signal plus the quantization error or the error signal, and this is our quantized input to predictor. Okay, so this is how this predictor would work in this differential pulse code modulator to generate the quantized error, which will be encoded to generate the Dpcm code. Okay, so here are some of the advantages of Dpcm over the pulse code modulation system. So bandwidth requirement of a differential pulse code modulation is very much less in comparison to PCM, as we are using a fewer number of bits to represent our quantized error instead of the sample values, quantized samples. So quantization error is reduced due to the use of prediction filter. So error is also less in this system because of the prediction filter we are using, and number of bits used to represent one sample value are also reduced. So both first and three points are analogous to each other, as the number of bits required are reduced, hence the bandwidth would also be reduced. So let's see some of the applications of Dpcm. The Dpcm technique mainly used in speech, image and audio signal compression. So it is used in signal compression basically. As we can see, if we were using the PCM, the bandwidth requirement or the number of bits to represent a sample was high, but in Dpcm we have reduced the number of bits to represent samples. Hence we have transmitting the same information now using a fewer number of bits. So hence we have compressed our signal. So this method is suitable for real-time application of medical imaging such as telemedicine and online diagnosis. So it is used in telemedicine and online diagnosis as well. It can be efficient for lossless compressions also. Okay, so this is about the differential pulse code modulation, which is an extension of the pulse code modulations. Now let's see delta modulation. So it is a differential pulse code modulated scheme in which difference of the signal is encoded in just one bit. So in this modulation technique we will reduce the number of bits to further low. Okay, so the difference of the signal is encoded in this delta modulation, and only one bit would be required to represent that difference. So we can also consider it as a extension of Dpcm and PCM. It performs better than PCM and Dpcm in terms of bandwidth or the data rate requirements, as it is having large information carrying capacity with the use of fewer bits. So again it will further reduce the requirement of bits to carry the large information. So delta modulation is a technique which provides a staircase approximation that we will see in the figure now. Delta modulation is a technique which provides a staircase approximation to an oversampled versions. By oversampled version we means that the sampling rate is much higher than the Nyquist rate. Okay, so in this, the linear differential modulator, the approximated staircase version of the sampled signal is compared with the original single, that is the current sample value, and the difference signal is produced, and this difference signal would be coded by using just one bit. So the difference signal is then quantized into only two levels, that is plus delta or minus delta. Delta was our staircase width. Okay, so corresponding to positive and negative differences. So it will generate the positive or negative delta depending upon the difference between the approximated staircase version of the sampled signal and the original signal or the current sampled value. Let's see in the diagram. Here we can see that it is the previous staircase version of our sampled input. So we have a previous approximation staircase which we have generated using a quantizer. Okay, and this is our current sample value. This is our current sample value. So we would compare both these. If the current sample value is greater than the previous value of the approximated staircase, that is, if this is the current value, let's see if this is the current value here, and it is greater than this previous staircase version, so we would have a 1 over there. Similarly, in this case, if this current value, sample value, is greater than the previous staircase version value, then we will have 1. So similarly, we can convert this difference. If the current sample value is greater than the previous staircase version, then we would have a 1, otherwise we would have a 0. So if the approximated signal lies below sampled x and ts, then the approximated signal is increased by plus delta and vice versa. If this x and ts, that is the previous case approximation staircase value x and ts is lies below, that is it is less than the approximated signal, then we would need to add plus delta in it, and if it is more than that, then we will add minus delta. So this scheme works well for small changes in signals values, hence sampling is done at a higher rate than the Nyquist rate. So if this is plus delta, there is a change of plus delta, the encoder will assign 1 to it, and if it is minus delta, then the encoder will assign 0 to it, as we can see in the block diagram. So this is a 1-bit quantizer we have, and a input to is the input sample x and ts. Okay, and this is our previous, or x cap nts, or u n minus ts is the previous staircased version of the sample. So this comparator or summer will compare both these values and provide us with the plus delta or minus delta. This error we will fed to the quantizer, 1-bit error. It will give us plus delta or minus delta, and the encoder would change this value to 1 if it is plus delta, that is the present value is greater than the previous staircase value, then it will provide us 1, and if the previous current value is less than the previous staircase value, then it will provide us minus delta. Okay, so this is the block diagram of delta modulator, which would generate only 1 bit for the difference between the previous and the current samples. So this is how it will convert the information into binary bits. Okay, thank you very much.